Dear students, Assalamu alaikum. Uh, I think we have two lectures left before the midterm examination, and in these two lectures I will focus on the questions and problems of the last two chapters we have studied, and I have already sent you hints on the questions and answers of these chapters. You better put these pages before you when you attend this lecture. Let me display the relevant pages here. Okay, this is the page number 415 from Ali Umar, and it is giving summary on the topics you have studied in this chapter. I would suggest that you better go to this summary very consistently, and so that you can recapture what has been stated in this chapter. Okay, so after you go through this summary, let me now switch to the question section. These are the questions on this chapter, for which I have sent you the hints. Question number 1 is: let A and B refer to two different atoms. Using symmetry arguments, determine whether the following types of molecules are dipolar or not. For example, AA. So you see that in this particular molecule we have two similar atoms, so there is a spherical symmetry present here on the charges. So this molecule will be non-polar. However, the next example, AB, in which we have two different atoms, and obviously there will be an electronegativity difference between the atom A and the atom B. So even if this molecule is covalent, it will have some ionic nature as well. So you will have the center of positive charge displaced from the center of negative charge for the molecule, and this is why this particular molecule will behave as a polar molecule. Okay, the next is the example ABA. Over here, although there are three atoms and one of them is B, so here if you have a rectilinear arrangement, it means even if A has a slight positive or negative charge, B has a slight positive or negative charge, and A has a slight positive or negative charge, but as a whole, ABA will be spherically symmetrical with reference to charge distribution, and there will be no displacement between the positive center and the negative center of this molecule. So this molecule will behave as a non-polar molecule. Similarly, you can discuss, well, in this triangular arrangement, I think I have written in my hints. Here is the page which I have already sent, so you better go through this page, these pages, so that you are able to answer this particular question. Okay, now question number 2: the static electric constant of water is 81 and its index of refraction is 1.33. What is the percentage contribution of ionic polarizability? So for this question we have to use an equation mentioned on page 416. So let me go to this equation. This is page number 416. Well, I have written this particular equation as is referred here over here. So let me go back to the questions of this chapter. Okay, this is the equation I was mentioning, not this one. It is equation 416, page number 416. Well, this is the page which I wanted to refer, but I can't see the equation here. Now where is this equation? Perhaps I have given the wrong page number, but let me find this equation for you, which is going to be used here. Yes, this is the equation. So we will use the equation for ionic polarizability given by epsilon r at 0 temperature minus n square. So here you will substitute the values of the data given in the question, and you will find the ionic polarizability by using this equation. Okay. So where epsilon r0 is the static dielectric constant as given, equal to 81, and index of reflection is n is equal to 1.33. So complete these calculations. So that will be the that is the answer to the question number 2. And let me go back to question number 3 here. Well, I think these are the two questions I wanted to discuss. And let us now move to the problem section. Okay, for problem section, you will have to switch to page number 2 of my notes already sent to you. This is page number 1, and this is page number 2. So here is the problem number 1 solved, and the statement of the problem. Let me give you the statement. Using Coulomb's law, derive the expressions 8.2 for the field of an electric dipole. Assume that T is much less than R. So I have given the hints of this over here. See this derivation in any book on electromagnetism. The topic will be dielectrics. So this derivation is a basic one, and you can find this derivation from any book on electromagnetism. Now for problem number 2, this is problem 2. Derive equation 8.3, that is, show that the torque exerted on a dipole P by a uniform field E is given by torque is equal to P cross E. Now this I have again given you the hints on the same page, page number 2. The force as shown is equal to Q into E and displacement is D, so the torque will be Q D into QE, which is the force into the displacement, and when we rearrange this, we get this torque equal to P cross E, as dq is equal to the dipole moment. Okay, so that is the solution to the problem number 2. And for problem 3, well, you can also discuss the B part of this problem. This regards the potential energy, and the potential energy you will have to take the dot product. Here we have taken the cross product, but for the potential energy we will have to take the dot product, and the potential energy is negative because it is attractive, and therefore you can solve this, you can derive this equation as well. Okay, for problem number 3, the dipole moment, sorry, problem number 4, you skip to problem number 3. Let's go to problem number 4. Determine the dipole moment for the following charge distributions, 1.5 microcoulomb each at the points 0, 3, 0, 5, where the coordination numbers are given in, where the coordinate numbers are given in centimeters. So the solution, the hints on solving this problem is given here. You will have to move to the next page, and this is the next page. This is page number 2. So here is the problem number 4, in which Q is this, T is this, and dipole moment is equal to P is equal to Q into D. So you simply substitute the values and do the calculations in the same coordinate system. That is, you must use the displacement in meters and the force in SI units. Okay, similarly for problem number 5, a parallel plate capacitor of area this is filled with mica. The distance between the plates is 1 centimeter, and the capacitor is connected to a 100-volt battery. Calculate the capacitance of this capacitor. We will use a very basic formula for the capacitance here. You know that capacitance C is given as epsilon R A over D, where epsilon R is the dielectric constant or the relative permittivity, A is the area of the capacitor plate, and D is the distance between the two plates of the capacitor. So you put up the given data and calculate the capacitance. And similarly, the parts B and C and D are very simple, very basic, and you must calculate these parts as well. You will have to consult any book on electromagnetism to find the free charge on the plates, to find the formula for the free charge on the plates, the surface charge density, etc., and you will be able to solve this problem. Okay, so that was about chapter number 8. Let us now move to the questions and problems of chapter number 9. Okay, so let me move on to you will again go through the summary of this chapter before you solve the questions and answers. The summary is given page 487. So let me see where is this page 487. This is 542. We have crossed that portion. Let me go back and go to page number 487. This is 419. So I will go there quickly to page 487. A little bit more. Here is the summary at page 487. So you must go through this summary so that you can recapitulate whatever you studied in this chapter up to the topic Langevin paramagnetism and ferromagnetism. Okay, so after going through this summary, then you go to the question section. Where is this question section? These are problems and these are questions. So question number 1, the text stated that the diamagnetic response associated with the orbital motion of the atomic electrons can be predicted on the basis of Lenz's law. Prove this statement. So go to the page number 3 of my notes. So here I have discussed this. Lenz's law in electricity states that the voltage, that is the induced EMF, opposes the cause which produces this. And same is the story with diamagnetism, orbital diamagnetism. It is the same thing but stated in dielectrics, in magnetism, sorry. So orbital diamagnetism is exactly consistent and has a similar state in magnetism. So if you want to elaborate this answer, you can do that. Okay, now question number 2. Do you expect the constant lambda in equation 9.30 describing the susceptibility of the covalent bond to be positive or negative, and give the reason why? So this I have also discussed here. Chi is equal to chi I plus lambda. That is the equation which states if the bonding is covalent, that is due to the sharing of electrons, and it will add to chi and have lambda should be positive. So what I am saying here is that for covalent bonding, the total susceptibility must be equal to chi I, which is the susceptibility due to the core electrons apart from the outer electrons, and this is the susceptibility due to the outer electrons, which induces sort of ionic nature to the molecule. And so the total susceptibility, magnetic susceptibility will be more than chi I, so that's why lambda should be positive. Okay, so next question is question number 5. Given that the precessional frequency due to spin-orbit interaction is 10 gigahertz, estimate the effective magnetic field experienced by the spin moment as a result of this interaction. So this I have also given the hint over here. So go through this hint. You will use equation 9.10 for the precessional or Larmor frequency omega L is equal to EB over 2m, and use the data given and calculate the value of this precessional frequency. Similarly, question number 6, referring to question 4 and 5, estimate the temperature above which the simple formula breaks down. No, I think the number I have mentioned is not 6, it should be 7. So this is question number 7. Give a sufficient condition for the existence of paramagnetic susceptibility in terms of the number of electrons in the atom. Well, you know it very clearly that for the paramagnetic behavior we should have number of in the outer shell we should have few unpaired electrons, so that is the sufficient condition as I have mentioned in the answer. Okay, now to the problem section. I would suggest that you go through problems number 1, 2, 3, 4 and 5. Now again you will have to find the formulae from the main text of this chapter to see which formula is to be applied to calculate what is being asked. So you will have to focus on the formalism and you will be able to solve these problems. So okay, that's all for today's lecture, and you must go through whatever has been told today. Okay, thank you very much.